Bondini. Well, that's the way we say hello in Papiamento, the local language of Aruba. Hello, children. How are you people doing? I'm Saurabh Kumar Dutt, and I'm here to teach you people a little bit of mathematics. Now, children, this scintillating place that you get to see is the Palm Islands in Aruba, South America. It is here that you get to do some guided snorkel tours in the local tropical reefs. You get to do some banana boat rides, some magnificent water park rides, and when you feel hungry, the hot buffet is ready for you. Make sure to have the local sweet dish, which is casillo, and also to say all the people of Aruba that you get to meet, Bon Bini. In this note, children, I'm going to start off this lecture, which is about trigonometrical identities. Here we get to learn a facet in trigonometrical identities, which is elimination of the angle theta, or elimination of any trigonometrical ratio which is there given in a couple of equations. So now first I will give you the basics as to how we do this, and then after that we have some questions waiting for us, which we will discuss in detail so that any question which comes your way, you will easily be able to deal with it. Now here, children, I like to tell you one thing more. After we have this lecture, you will find that as the first message or as the first comment, you will get to see the link in which you can study the whole lecture in detail, which contains proving trigonometrical identities, elimination of the angle theta, and also solving trigonometrical equations, which is in the syllabus of class 10. Further, if you look up the description of this lecture again, then you will get a link which will provide you the full scape of all the lectures which are available. So make sure to access all of that and make your maths perfect. Now, children, progressing with the lecture and looking up here how to deal with such sort of questions. Now, I'm sure you people must recognize these square trigonometrical identities which we have, that is sine square theta plus cos square theta is equal to 1. Then we have cosec square theta minus cot square theta, which is equal to 1. And then we have sec square theta minus tan square theta, which is equal to 1. So we have these square trigonometrical identities where you get to see one special thing, that is, on one side we have trigonometrical ratios and on the other side we have none. So as such, somehow the other that we can get to the left hand side, we can easily eliminate the trigonometrical ratios, right? So this is what we're going to try out in the different sums. Now, discussing the first sum with you people, we have to eliminate the angle theta in these two equations which have been given to you. Like normally I do, I'm going to give you 10 seconds for trial. If you require more time, then you can pause the lecture further and give it a bigger try. Okay, children, now discussing the sum with you people. Here we've been given that we have to eliminate the angle in x is equal to a sine cube theta, y is equal to b tan cube theta. So as you see in the three square trigonometrical identities that we had sine cos, cosec cot, sec tan. But here what we have is we have sine and tan, and as sine and tan don't form a couple in each of these trigonometrical identities that we've just studied, so somehow or the other we've got to transform them so that we can get to any of those three trigonometrical identities, which is the only route to elimination of the angle theta. So first what we are going to do is, first now we are going to talk about trying to make these equations a little different so that they come to be in that square trigonometrical identities format. Now we first talk about the equation x is equal to a sine cube theta, and here, children, what you can do is you can write this to be x upon a to be equal to sine theta, right? Now sine cube theta. Now we've got to get to sine theta. As such, next now what we do is we'll be taking cube root of both the sides. So now taking cube root, what you do is this is then going to become equal to x upon a whole raised to the power 1 upon 3 will become equal to sine theta, right? Now, as you know that the inverse of sine is cosec, so we will try and bring cosec, because the inverse of tan similarly that we can get is cot, and cosec square theta minus cot square theta will give us 1. As such, we will try and bring the inverse of sine theta, and that we can do by taking invertendo. Now, what is invertendo? It is that if you have a proportion already, right, that is a upon b is equal to c upon d, as the sign of the proportionality is the same as the sign of equality. When we talk about this invertendo, which we've just discussed, then the denominator becomes the numerator and the numerator becomes the denominator in both sides of the equation. And this, children, is invertendo, is what we are going to now apply. As such, now we will have a upon x whole raised to the power 1 upon 3, which will become equal to 1 upon sine theta. I'm sure you people know that the inverse of sine theta is cosec theta. As such, cosec theta is now going to become equal to a upon x whole raised to the power 1 upon 3. Now, after this, children, we are now going to square both the sides. So, squaring, we now get to a upon x whole raised to the power 1 upon 3 whole raised to the power 2, which becomes equal to cosec square theta. Now, further, children, after this, next what we do is, as we know that if we have a raised to the power m, which is whole raised to the power n, then by applying the rules of indices, we get it to be a raised to the power mn. As such, here this will become a upon x whole raised to the power 2 upon 3, which is equal to cosec square theta, and we can mark this to be equation number 1, right? Now, children, we come over to the second equation that we have at hand, and that is y is equal to b tan cube theta. So y is equal to b tan cube theta is the next equation which is going to be tackled. So first we keep the trigonometrical ratio alone by its side. That is, we have y upon b, which can be written to be equal to tan cube theta. So like we did in the last case, we are now going to take cube root of both the sides. So taking cube root of both the sides, now we will get to y upon b whole raised to the power 1 upon 3, which becomes equal to tan theta. Now, after that, next what we're going to do is we require the inverse of this. As such, next now we're going to apply invertendo. And when we talk about invertendo, then on the right hand side we will get here cot theta, right, which is going to help us with cosec theta, right? So now we will get b upon y whole raised to the power 1 upon 3 will become equal to 1 upon tan theta, and since you know that 1 upon tan theta is the same as cot theta, so the right hand side becomes equal to cot theta and the left hand side is b upon y raised to the power 1 upon 3. Now in the next step we will be squaring both the sides. So squaring both the sides, next now we get to b upon y whole raised to the power 1 upon 3 whole raised to the power 2 becomes equal to cot square theta. Next now, children, this becomes b upon y whole raised to the power 2 upon 3, which becomes equal to cot square theta, and this, children, is now the equation that we're going to use as equation number 2. So further now what we do is, if say from equation number 1 we subtract the second equation, then on the right hand side we will get cosec square theta minus cot square theta, which will give us 1, and thus the trigonometrical identity will get applied. Cosec square theta minus cot square theta is equal to 1, and theta will be eliminated. So we have a upon x raised to the power 2 upon 3 minus b upon y raised to the power 2 upon 3, which becomes equal to cosec square theta minus cot square theta. And here children, next what we can do is we can write this as a upon x raised to the power 2 upon 3 minus b upon y raised to the power 2 upon 3, which will become equal to 1. And this is because we know that cosec square theta minus cot square theta is equal to 1, and because of this we can write the right hand side to be 1, and thus we can say that the angle theta is eliminated, right? So this is all that we've got to do in this question. Now children, quickly discussing the question with you people once more, so that if there is any doubt whatsoever, all of that gets removed. In the question children, we've been given here that we have to eliminate the angle in x is equal to a sine cube theta, y is equal to b tan cube theta. Right, so here what we do is we can now bring in the first equation a to the denominator of the left hand side, thus transposing this we will get sine cube theta on one side, which in times to come is going to become handy. Now further we will take cube root of both the sides, thus we have x upon a whole raised to the power 1 upon 3 will become equal to sine theta. Now since in any of the three square trigonometrical identities that we have, sine and tan don't come together, as such we will try and get the inverse of them, that is cosec and cot, which we know that cosec square theta minus cot square theta gives us 1. So here as such, after taking cube root, next now we're going to talk about invert endo of this, that is we will write the numerator to be the denominator and the denominator to be the numerator. This is a property of proportion which tells us this, that if there is a existing proportion a upon b to be equal to c upon d, then invert endo being applied, the denominator becomes a numerator and the numerator becomes a denominator on either side of the equation. So this is what we've done here, that is x upon a now becomes equal to a upon x raised to the power 1 upon 3, which is equal to now 1 upon sine theta. 1 upon sine theta is cosec theta. Now further we square both the sides, and when we square we get on the right hand side cosec square theta, and on the left hand side we get something like a raised to the power m whole raised to the power n, which will become the product of m and n as is there in the indices formula that you have, that is a raised to the power m whole raised to the power n becomes equal to a raised to the power m into n. So applying this, we have a upon x raised to the power 2 upon 3, which becomes equal to cosec square theta. Now next, when we talk about picking up the second equation, which is y is equal to b tan cube theta, now here also we make tan cube theta the subject of the equation by transposing b to the denominator of the other side. Then we take cube root of both the sides, so that we get y upon b whole raised to the power 1 upon 3, which becomes equal to tan theta, that is now the power of tan theta is 1. Next now, as with sine theta, tan theta is not going to work, thus with the inverse of sine theta, that is cosec theta, we try and make to work the inverse of tan theta, that is cot theta. So as such, next what we do is we apply invert endo to this, and thus the denominator becomes the numerator and the numerator becomes the denominator in both the sides. Now 1 upon tan theta is cot theta, that is what we have on the right hand side. Then we square both the sides so that we can get to cot square theta. So cot square theta becomes equal to b upon y raised to the power 2 upon 3. Now if from the first equation, which is in terms of cosec square theta, we subtract the second equation, which is in terms of cot square theta, so cosec square theta minus cot square theta will give us 1, and on the left hand side you will get a upon x raised to the power 2 upon 3 minus b upon y raised to the power 2 upon 3, right? So here we get to see that since cosec square theta minus cot square theta is equal to 1, we've been able to eliminate the angle theta or any trigonometrical ratio from the equation, and this children is what we had to do in this question. So is everybody clear about this? For sure. That's good. Now after this children, next now we'll be discussing a little higher order sum. I'd like you people to give it a good valiant try, after which I'll be discussing the sum with you people. I'll give you 10 seconds for trial. Okay children, discussing the sum with you people here. Now we've been given that we have to eliminate the angle, or we've got to eliminate any trigonometrical ratio in the two equations which we've been given. So one is cosec x minus sin x is equal to a cube, and the second is sec x minus cos x is equal to b cube. Now in the first equation we have cosec x minus sin x, and we know that the inverse of cosec x is sin x. As such, now we convert cosec x to sin x in the first equation. First, copying the equation, cosec x minus sin x is equal to a cube. Now further, cosec x can be written as 1 upon sin x, as it is the inverse of sin x minus sin x, which becomes equal to a cube. Now further, when we take an LCM, the LCM will become sin x in the denominator, and in the numerator we have 1 minus sin square x. And remember children, if you talk about sin square x plus cos square x, as you know, that is equal to 1. This further implies that if you talk about 1 minus sin square x, you have cos square x, and thus we can replace this as the numerator. And obviously in the right hand side we have this as a cube, and thus we have cos square x divided by sin x, which is the value of a cube, right? Now here we have this equation where we can find out the value of sin x in terms of cos square x, right, which in times to come is going to be handy. So what we do next is, now we make sin x the subject of the equation, and we can have its value in terms of cos square x. So as such, sin x will become equal to cos square x divided by a cube, and this children can be marked to be equation number 1, right? Now after this, now next what we do is we talk about the second equation that we've been given, and the second equation that we've been given is sec x minus cos x is equal to b cube. So sec x minus cos x has been given to us to be b cube. So further simplifying this, as we know that the inverse of sec x is cos x, so we write this whole equation in the form of cos x. So we have 1 upon cos x minus cos x, which becomes equal to b cube, or in other words we have 1 minus cos square x divided by cos x, which becomes equal to b cube. Now after that, next what we can write this as, again we quickly are reminded of the formula that we have sine square theta plus cos square theta, which is equal to 1. As such, here we can now make sine square theta the subject of the equation, and thus we will have 1 minus cos square theta on the other side. Now as here we have 1 minus cos square x, we can write it as sine square x, and in the denominator we have cos x, and that thus becomes equal to b cube, right? Okay, now here children, again we can make cos x the subject of the equation. As such, cos x is going to become equal to sine square x divided by b cube, and you can mark this to be, say, equation number 2, right? So remember here, from the earlier equation we already have the value of sine x, which we can substitute in the second equation. So now the value of sine x, which is cos square x upon a cube, is going to be substituted in the first equation. The second equation. So we have sine x, which is equal to cos square x upon a cube, which is the first equation, right? And this value of sine x is going to be substituted in the second equation, cos square x upon a cube, right? So this is the next step that we write, that is substituting sine x from equation number 1 to equation number 2. Remember, writing a little bit of steps always removes the confusion from the teacher's mind as to what you've done next, and thus you get better marks. As the teacher understands, when the teacher understands, the teacher gives you marks. So now we substitute the value of sine x in equation number 2, which now becomes cos x is equal to, in place of sine x we can now keep cos square x upon a cube, right? And as there is a square, so we square it and we divide it by b cube. So for the next children, this becomes equal to cos raised to the power 4x divided by a raised to the power 6 whole raised to the power b cube, right, which is equal to cos x. Now further, the right hand side is a mix up, so we will now write this as cos raised to the power 4x divided by a raised to the power 6, further divided by b cube, as this line is the whole denominator sign. So further we can get this as cos raised to the power 4x divided by a raised to the power 6 into 1 upon b cube when we convert the division sign to multiplication sign, and then we write the reciprocal of the term which comes after the division sign, and this is cos x. Now 1 power of cos x gets cancelled from both the sides. As such, you can say now that cos cube x will become equal to a raised to the power 6 into b raised to the power 3, or in other words, we have the value of cos x, which is all in terms of a and b, that is a square b. Now this obviously has been done by taking the cube root of both the sides. So that is what we write here, that is taking cube root, we get to this. Now the same process, children, we're going to do for the other equation, that is the value of cos x is now going to be supplied to equation number 1, right? So from equation number 2 we will be supplying this value to equation number 1. Cos x is sine square x upon b cube. So this value is going to be supplied, or substituting cos x from 2 to 1, right? Now cos x, children, is how much? It is sine square x upon b cube. We will write both these equations to remove any confusion. Cos x is equal to sine square x upon b cube, and then we write the first equation, that is sin x is equal to cos square x upon a cube. Now this, children, is the first equation, and the above was the second equation. Now we require to substitute this value of cos x in the first equation. As such, next now we will have the second equation to be transformed as cos x is equal to the value of sin x. We have to keep the value of sin x in the second equation, as we've already done this of keeping the value of sin x in the second equation, right? So the value of cos x is going to be substituted to the first equation, right? So when we keep the value of cos x in the first equation, we will now have to keep the value of cos x, that is sine square x upon b cube, right, in the second equation. So this value now will thus become in the second equation, in the first equation, as sine x is equal to, in place of cos x now we have sine square x upon b cube, right? And we also have to square this, as there is cos square x, right? And further now this is divided by a cube, so we divide this by a cube. Now this was equation number 1 in which we brought the changes. So further now we have sine x to be equal to sine raised to the power 4x divided by b raised to the power 6 whole divided by a raised to the power 3. Again, as we have one fraction divided by another fraction, so we will write this as sine raised to the power 4x upon b raised to the power 6 divided by a cube, and further that can be written as sine raised to the power 4x upon b raised to the power 6 into 1 upon a cube, right? And further then we get to see that on the left hand side we have sine x, so 1 power of sine x gets cancelled from both the sides, and thus we can now write sine cube x, which becomes equal to a raised to the power 3 b raised to the power 6. Now children, we require to take cube root of both the sides, so taking cube root, we will now be able to get to the value of sine x. So further, sine x becomes equal to a times of b square, right? After we have this, now we have the value of sine x, we have the value of cos x. We'll mark this to be equation number 4. Earlier we had equation number 3, right? Now this value of cos x can be marked to be equation number 3. We have equation number 4. Now what we're going to do is we will be squaring the third equation and the fourth equation and adding them. So now we write that by third equation square plus fourth equation square and adding it. Now when we do this step next, we have cos square x on the left hand side of the third equation plus sine square x on the left hand side of the fourth equation, which becomes equal to a square b whole square plus ab square whole square, as sine square x plus cos square x is equal to 1. So this value is what we replace on the left hand side, right? And thus our left hand side becomes free of any trigonometrical ratio. The right hand side is already free, and thus children, here what we have is we now have 1 on the left hand side, and that is equal to a raised to the power 4 b square plus we have a square raised to the power 4, right? And here we can further take a square b square common outside, and then we have further here a square plus b square inside, and here you can say that theta has been eliminated. That is, the angle has been eliminated. So this is what had to be done in this pair of equations. Now children, I'll just quickly discuss the question all over again, and whatever is a doubt, you will get it cleared in the second explanation. So focus to where my pointer is, right? Now in the question children, you've been given cosec x minus sin x is equal to a cube, sec x minus cos x is equal to b cube. You've got to eliminate the angle x. Remember, this is a very important question for your examinations, so focus completely here till the end of the explanation. Then make sure that you do a practice so that this is confirmed with you, that if this is asked in the examination, you're able to do it well. Now the first equation is cosec x minus sin x is equal to a cube. So here what you do is you can write this cosec x as 1 upon sin x, as the inverse of cosec x is 1 upon sin x. Next, now when we take an LCM in both of these fractions, we have 1 minus sin square x upon sin x. Remember, sin square x plus cos square x is equal to 1. As such, 1 minus sin square x will become equal to cos square x, which can be now replaced in the numerator. So you have cos square x divided by sin x, which is equal to a cube, and thus from here you can find out the value of sin x, which is cos square x upon a cube, which in times to come is going to be handy. Now after this, what we do is we pick up the second equation, which is sec x minus cos x is equal to b cube, and here we can write sec x to be 1 upon cos x, as the inverse of sec x is cos x. Further, when we take an LCM in both of these fractions, we have 1 minus cos square x upon cos x to be equal to b cube. Again, we are reminded of sin square theta plus cos square theta to be equal to 1. So 1 minus cos square theta can be written as sin square theta, right? So this is what we can replace in the numerator. So we have sin square x divided by cos x to be equal to b cube. So further, cos x becomes equal to sin square x divided by b cube. Now here we have the second equation, and the first equation was sin x is equal to cos square x upon a cube. So now this value of sin x from equation number 1 is going to be substituted in equation number 2. That is, for sin x here we'll be writing cos square x upon a cube, right? And in the denominator we have b cube. As this is one fraction upon another fraction, on squaring we get cos raised to the power 4x divided by a raised to the power 6, right? And this division sign can be written as the division sign that we normally have in maths. That is, the whole denominator sign has been written like division sign, as both of these confer the same meaning. Then the division sign is converted to multiplication sign, and the term which is after it, its reciprocal, is written as you normally do in maths. Now further, here 1 power of cos x gets cancelled from both the sides, and thus you have 1 to be equal to cos cube x upon a raised to the power 6 b cube. Now further, this a raised to the power 6 times of b cube is cross multiplied to the other side. Now when you take the cube root of both the sides, it become cos x is equal to a square b. Now when you substitute the value of cos x from the second equation to the first equation which you earlier had, right? Now the second equation has cos x to be sine square x upon b cube. We substitute this in the first equation, right? So this is what we are going to do. So we'll write sine x, right, which is equal to the value of the value of cos x that we have, that is sine square x upon b cube, right, and we square it and divide it by a cube. So here what we are doing now is we are substituting the value of sine x in the first equation, right? So here for sine x we have this value cos square x upon a cube that we have substituted, right? And further now substituting this value, we now have sine x to be equal to sine square x upon b cube whole square, right? In place of cos square x, remember, we have substituted the value of cos, which is sine square x upon b cube, right? And then further we divide it by a cube. Now when we square this becomes sine raised to the power 4x upon b raised to the power 6 divided by a cube. Now as this is the whole denominator sign, we write it by the division sign, as both of these have the same meaning. And further then we get to see that we can now write the division sign to be the multiplication sign, and the term which comes after it we can write the reciprocal of it. Further, one part of sine x gets cancelled from both the sides, and thus sine cube x can be written as b raised to the power 6 times of a cube. Next now we take the cube root of both the sides, and thus we get the value of sine x to be ab square, right? Now after we get the value of sine x to be ab square, we already have the value of cos x, remember, as sine square x upon we have the value of cos x as a square b. So when we square the third equation and we square the fourth equation and add them, we will get cos square x, right, on the left hand side, plus we will have sine square x on the left hand side, which will become equal to a square b whole square, right, which is the right hand side of the first equation, plus a b square whole square, right, which is now the right hand side of the fourth equation. And now we have this next equation where sine square x plus cos square x will become equal to 1, as we know it by trigonometrical identities, and on the right hand side we have constants. As such, on solving this further, we can take a square b square common outside, and then we have a square plus b square inside, and this shows that this equation no more has a trigonometrical identity, right, nor does it have any angle, and thus we can say that the trigonometrical identity has been eliminated and the angle also has been eliminated. And this is, children, what you had to do in the sum. So is everybody clear about this sum? For sure. That's good, children. Now after this you require to practice all of these sums, so that in times to come, when such sort of sums come in your examination, you're able to do it really well, right? So bye, children, have a nice time and do practice such sort of sums. Bye.